Welcome, everyone. Before I begin, just a note that this presentation represents my personal experiences and opinions and not necessarily those of my employer, past or present. I'm currently employed at Tesla, working on software systems for renewable energy generation, battery storage, electric vehicle charging, and energy market participation. I'm going to talk today about WebAssembly, a technology that I think is just maturing right now to the point where we should start considering it seriously in IoT as well as ICS, giving us a cleaner separation between firmware and software, allowing us to iterate faster, respond faster, and also do so more securely. So I'm going to begin the presentation by kind of motivating my interest in WebAssembly through some of the problems I'm facing at the IoT Edge as well as in the cloud. Then I'll provide an introduction to WebAssembly. Then through a motivating example, I'll describe what it would be like to be an application developer using WebAssembly. And finally, I'll conclude with some challenges. So let's start by looking at some challenges in edge computing environments that I think WebAssembly can help address. And what I mean about my definition of edge computing, I guess, I'm going to talk throughout the presentation about the edge or the IoT edge. Really what I mean is software or firmware controlling hardware performing critical functions. So I think what I'm going to talk about here equally applies to ICS, to manufacturing, or any kind of software in critical infrastructure. Okay, so let's take a look first at what it takes to get software deployed to an IoT edge device. So first you need to write that software, compile it, test it, do static analysis. Then you need to package it for deployment, including signing, go through component testing, integration testing. You often have procedures for regulatory compliance or customer acceptance testing. And then finally, you get to this stage where you can distribute it to those IoT edge devices. And the distribution is often phased around the world in order to monitor it and protect against regressions. And often in these environments, you need to obey some kind of maintenance schedule that's dictated by the customer. And some of these edge IoT devices are air-gapped in some of their functionality, so they may be able to send telemetry to the cloud, but you can't actually update firmware or do control against them. So they're actually updated quite infrequently. And what this means is this whole process can take weeks, months, or years to deploy new code to edge IoT devices. And because this process is not executed very frequently, we don't get very good at it as an industry. And because we're not good at it, people sense risk, and they don't want to change. So I think WebAssembly is an opportunity, perhaps, to iterate more quickly here, but also do so more securely. OK, there's 3 problems I'm facing in the cloud that I think WebAssembly may help address. The first is hosting untrusted code. For me, that's usually empirical models that are developed by other teams that I need to host in my infrastructure. So there are some service providers that are kind of on the cutting edge of WebAssembly usage. Cloudflare and Fastly are both hosting untrusted code from their customers and then moving it around their global networks to operate closer to their customers. And Red Panda allows the opportunity to host like data transformations and streaming calculations using WebAssembly. The second problem that I'm facing in the cloud, the relationship between edge IoT devices and cloud services to date is a fairly simple one. So edge IoT devices send telemetry and alerts to the cloud, and they fetch their configuration, and that's about it. And then really rich services for asset management, stream data processing, historian capabilities, data lakes, security, really only exists in the cloud environment. So in order to build really sophisticated services, I think we need to start blurring the distinction between edge and cloud and having some of those sophisticated services move closer to the edge. There's a few advantages in doing this. There's an opportunity to save a lot of money because you can take advantage of this edge computing environment that's essentially free. The edge usually has all of the context that it needs. Where in the cloud, if you try and recreate context, you often have to join data streams. And when those are eventually consistent data streams, that can lead to a lot of problems. And then the edge, if you can deliver these services on the edge can operate autonomously, even without its connection to the cloud. And you can offer much richer services doing this. This problem for me also goes the other way. I want to take code that's running on the IoT Edge and run it in the cloud so that I can, say, run a state machine representing a digital twin in the cloud, running the same code that's on the edge. Or perhaps I want to backtest models, like a pricing model, against historical data, where the same code is being used for that backtesting. And I see WebAssembly as starting to blur the distinction between edge and cloud, allowing us to move code from the cloud to the edge, or from the edge back to the cloud. Okay, and the third problem that I'm facing in the cloud that has motivated my interest in WebAssembly. So this, maybe 10 years ago or so, we're managing everything in the stack, all the way from hardware to the operating system up into the application. And then we virtualized the hardware, allowing us to run multiple operating systems on top of it. And then came containers, declarative deployments, orchestration, and so on. And this is where most companies operating the cloud are today. And it's a model that works quite well, but there are some problems if we look inside those containers. So if we look at a container, it's probably pinned to some kind of Docker image. You've probably installed some root CA certificates, along with some tooling. And then you finally get to the application binary itself that's embedded in this container. And let's say that that application has an HTTP server, which also means it has a library for parsing JSON and serializing JSON. Perhaps the application also exposes a gRPC endpoint. This application may publish event data to some kind of message bus like Kafka, so it's going to have a client for doing that. Of course, you want to monitor the health of this application, so it's going to have some kind of library and endpoint where you can do that. If this application persists state, it may be deployed alongside another container that has a database in it, which also means you then have a client for interacting with the database. And once we've laid all of this foundation, we finally get to the piece of business logic that we wanted to write called the application. Now, this isn't so bad when you have a handful of applications, but it gets really difficult to manage when you have hundreds of services like this. And these services some of them might be inherited from other teams. Some of them might include legacy code. They often have a mix of programming languages, a mix of libraries. And so if there's a security vulnerability in a certain version of the HTTP server used by some applications, which applications need to be patched, rebuilt, redeployed? Answering that question can be quite difficult for most organizations. This was the problem many people faced with the Log4j vulnerability. So this is really a problem of concordance, where we want to provide consistency, but also allow diversity, but still understand what's where, and have teams operate in a decoupled manner. So in order to address this concordance problem, I expect this trend to continue, with more and more application code moving down into the infrastructure. So what this would look like is, say, the HTTP server or that library that's parsing JSON moving down into the infrastructure and being managed there so that it can be consistent and so that it can be patched without involving application developers. This is very similar today. If you operate a Kubernetes cluster, you can patch the machines underneath the Kubernetes cluster without involving application development teams. It's really kind of a continuation of that. This was kind of the promise of serverless and functions as a service. I don't think it quite got there yet, and we need to move more and more code that's embedded in there down into the infrastructure. And I don't have time to go into it here, but if you're kind of intrigued by this model, this Wasm Cloud project is really leading the way here in terms of the model, the functionality, and security in this space. Okay, so I've kind of motivated why I'm interested in WebAssembly. At the edge, it's this problem of being able to iterate quickly, but also do so securely. And in the cloud, hosting untrusted code, having more and more of the application code move down into the infrastructure so that it's more manageable, and then this blurring of edge and cloud, where I can move services between the two. So now that we've done that, let's look at what WebAssembly is. So WebAssembly is a portable binary intermediate language that can be targeted from various programming languages and execute on different platforms, meaning it's portable, in a virtual machine. WebAssembly was first released in 2017, and it is supported by all of the popular web browsers. It was originally developed to enable high-performance applications in the browser, So that meant you could write really efficient code in C++ rather than in JavaScript and still execute it in the browser. There's also some kind of famous examples of legacy code being ported to the browser, like Google Earth, using WebAssembly. Now, I am not interested in web development at all. I've never written a line of code of JavaScript. My interest in WebAssembly has come in the evolution of WebAssembly to now be interesting in cloud environments as well as edge IoT computing environments. There's a number of systems programming languages that can target WebAssembly. So C, C++, C#, Rust, Go, Swift, and Python can all be compiled to WebAssembly. And the way it works is you write code in the programming language of your choice. You compile that to a WebAssembly binary, and then you host that WebAssembly binary in your application binary. And the WebAssembly itself executes in a sandbox. And the host application here is in full control. So it's a deny by default model where the application has to grant access rather than restrict access. And the basic instruction set of WebAssembly doesn't allow anything more than pure functions. So just math on memory. That's basically all you can do. So that means that the WebAssembly that's running in that sandbox, it can't open ports, it can't read or write files, it can't read or write shared memory. The application can also budget the number of instructions that the WebAssembly can execute or limit the amount of memory that can be used. And just before I move on, there's been a lot of work that many have done to sandbox applications already, right? Like secure boot, AppArmor profiles, C groups, your Docker environment, all these kind of things. That remains complementary to the WebAssembly sandbox. WebAssembly is really a sandbox even further inside the application that's right around the WebAssembly itself. So V8 is the WebAssembly execution engine and sandbox that runs both in Node.js and in Chrome. There have been attempts to move V8 into other environments, although what's become more popular recently are these client runtimes that you can use as a library. And there's been an explosion of these. There's probably between 10 and 30 of them. And there's a lot of innovation happening here. They're evolving very quickly. And I'll show an example later in the presentation. There's two other things worth mentioning about WebAssembly. The first is this WebAssembly Systems Interface, or WASI. So with such a limited instruction set in basic WebAssembly, this is an extension where you can do things like open ports or do file I/O. I'm not interested in WASI at all. I'm really only interested in WebAssembly for pure functions, as I'll show later. Another thing I am interested in is this component model. So this is the idea of declaratively composing WebAssembly modules in order to make useful services or applications. So an application may need a key value store in order to store state. So it would just declare that, and that could be provided in the infrastructure without the application developer caring how it's implemented. I think there's also some wins here potentially for SBOMs so that we could develop them around application capabilities, not just around the library versions that they're using. And it would work well with machine automation. Okay, changing gears a little bit. I want to demonstrate now through some source code what it would be like to be an application developer or service provider using WebAssembly and some of the advantages that come from it. So in order to do that, I'm going to use a motivating example of this point of sale terminal where it calculates the total price for a number of items, displays that to the customer before accepting payment. And the example is a little bit contrived, but I wanted something that's fairly easy to digest as part of this presentation. And I'm going to begin using a kind of traditional approach to software development, and the programming language I'm using here is Rust. So here's the function that calculates the price, and it's quite simple. It just takes the count of items and multiplies by the unit price. And then here's how it's used. So here the count and the unit price are hard-coded, but in the real world, those would be external inputs. It calls the price function to calculate the total price. Then it puts some restrictions around nonsensical prices. What I'm doing here is kind of hinting at firmware code that would protect against bad inputs. And this would be code that I would not be iterating on. And then finally, it returns the price. OK, so now that we've kind of laid the foundation, let's take a look at what it would be like to make a code change. So let's say we want to introduce off-peak pricing. So from 11 at night to 11 in the morning, we'll charge a different price. So we go back to the price function. And we're going to modify it now to charge the peak price during these hours, and then discount the price by half outside of those hours. And then we need to pass in now the hour of the day into our price function, but otherwise calculating the price is roughly unchanged. And now in order to deploy this to the point of sale terminal, we need to go through this long process that could take weeks, months, or years for this very, very tiny code change to reach our customers. Now let's take a look at this motivating example if we were using WebAssembly. So the first step to use WebAssembly in this motivating example is to extract the price function into a library. And the way we do that is just adding this no mangle and extern C around the function. And this just allows the library to be called from programming languages other than Rust. And once we've done that, we compile that Rust code into a WebAssembly binary. And then we need to load that WebAssembly binary into our firmware. And here I'm using the WasmTime client. So that's the WebAssembly binary there in a file being loaded. And then we're creating an instance of a sandbox in which that WebAssembly code will be hosted and executed. And then we're exporting from that sandbox the price function. And this is an example of how the host application is in full control of what is exported from the WebAssembly module. And then finally, we need to call that WebAssembly price function. So program looks pretty much the same as before, just with slightly different calling conventions around the price function because it's being executed in that WebAssembly sandbox. And a bit easier to compare side by side. This is our program before and after. So we do need to load that WebAssembly into the firmware, but otherwise, the only difference is really just this slightly different calling convention. Okay, now that we're using WebAssembly, let's take a look at what it would be like to make a small code change. So in addition to that off-peak pricing, let's also do happy hour pricing between 2 and 5 p.m. So we go back to our price function, and we modify it again to return the full price during a more restricted set of hours, and then discount the price by half outside of those hours. Because we changed the price function, we need to rebuild that WebAssembly binary. But then when we go look at the firmware, we don't need to make any changes. And this is really the kind of the key point of the presentation, is that I'm able to iterate on my price function and make changes to it without having to make changes to firmware, and I can do so safely and securely. That's the point, no firmware changes. Okay, so this raises some questions. How do we distribute that new code to that Edge IoT device? Now, the WebAssembly is only about 300 bytes, base 64 encoded, and it's pretty common that Edge IoT devices are managed through some kind of desired state configuration. So why not just take advantage of that? So it's not uncommon to have some kind of JSON document describing the desired state. In this case, it might have the language and the tax rate and those kind of things for the point of sale terminal. So we can just include the price function as signed base 64 encoded string in order to distribute it. And we can take this process that used to take weeks, months, or years for a very small code change to reach our customers, and we can choose to short circuit it at any point. And I would make the argument here that since the price function is a pure function, it can be entirely unit tested, that we could make that code change, repackage it, and redeploy it without going through component testing, integration testing, and the rest. Okay, before I conclude, some challenges and a bit of caution. Some people are going to object to changing code at runtime. The first objection I hear to that is security. But remember here, we are using WebAssembly. So it's running, first of all, the WebAssembly is signed. It's running in a sandbox with a very limited instruction set. And I'm also assuming that the firmware is already protecting against bad input and bad output. The next objection is around combinatorial testing. If you can change code at runtime, how are you going to test all these different combinations? I think this is a problem that already exists that sometimes gets ignored. Often Edge IoT devices have a large number of configuration parameters that change behavior, and you already have a combinatorial testing problem. So it doesn't really make it any worse. And then the third objection is tracking versions. So if someone calls your customer support line, how are you even going to know what kind of code they're running if it can change? Again, I think this is really just back to having a large number of configuration parameters that change behavior. You need to be able to track that well over time, and it's just motivating doing a good job at these things. Okay, picking a language can be challenging. So in systems programming, I really don't think we should be using C or C++ anymore. Those languages are just too dangerous. So if we're doing developing greenfield applications, I think we should stay away from those languages as an industry. Python is kind of awkward with WebAssembly because it's an interpreted language. The interpreter itself needs to go in the WebAssembly, kind of awkward. Go is a garbage collected language, so you need to deal with the garbage collection inside the WebAssembly. I think the clear winner is Rust for new development. Rust has really, really great tooling for WebAssembly. It's also a functional programming language, has lots of other benefits. If you're moving legacy code into WebAssembly, especially for hosting it in different environments, it may make sense to look at these other applications targeting it. But for new development, definitely look at Rust. Of course, there's lots of reasons to use Rust in ICS, in IoT environments. If you're not familiar with those motivations, I would recommend watching this talk from this conference from a couple of years ago. Okay, picking a runtime is actually quite challenging. As I mentioned, there's these whole number of client runtimes that you use as a library. The key here, you want a nice development experience for your developers, so nice interfaces, good documentation, those kind of things. But really key is that this is what implements the sandbox. So the integrity of this approach really comes from the integrity of that sandbox. And the reason we trust V8 in the browser is because of the scrutiny it's had over the years. And these runtimes have not had that level of scrutiny yet. I think the leader here is Wasmtime. Wasmtime is written in Rust rather than C or C++, like some of the other ones. And they've also been very, very open about their vulnerability disclosure policy, their use of cargo vet, which is in the Rust toolchain for securing their supply chain, limiting the use of insecure or unsafe Rust, fuzz testing, use of formal methods. And I think if these other runtimes are going to remain relevant, they're going to need to follow suit and with this kind of open approach. Okay, and the final kind of objection or piece of caution I get is, why not just use Docker to solve this problem? Or why not just distribute a binary to the edge? So at this conference last year, if you didn't see the SolarWinds Sunburst presentation, I highly recommend watching it. Very, very interesting talk. And really, that's teaching us that even trusted code can be vulnerable. So one of the real advantages with WebAssembly is it's a very, very limited instruction set. So it limits what you can do. You can't do much of anything. I think that is reason alone to be interested in WebAssembly for solving these problems. But even if that's not your cup of tea, if you have to deal with multiple environments, you're going to have to deal with portability. You might end up with pretty large containers or binaries. You need to deal with that problem. WebAssembly binaries are extremely small. They start really quickly. And if you're dealing with Docker updates, and depending on how you have your secure boot implemented, it can be really problematic to mix those two things together. So I think in the limit, if you're going to go and address these problems on your own, you're kind of reinventing WebAssembly and all the problems it's solving. So why not investigate WebAssembly first? I think probably also doing these things on your own rather than in a broader community, you're probably not going to do a better job. Okay, summing up. I think WebAssembly is really interesting because of its sandboxed, deny by default security model that puts the host application in full control, as well as its really limited instruction set. That's an advantage in terms of its security. It also has portability, so I can run the same code in the cloud, on the edge, in the browser, in a mobile environment, and it can do all that at near native execution. WebAssembly is really interesting in the cloud in order to take more and more application code and move it down into the infrastructure to make that more manageable, easier to patch. And I think it's very, very interesting in blurring the distinction between edge and cloud and allowing us to develop more sophisticated applications. Okay, so this is a bit of a food for thought presentation. I'm not actually using WebAssembly like this in any production environments, although I've been doing a lot of prototyping and proof of concept work around it lately. So if you're interested in this, please come talk to me. If you think the idea is crazy, please come talk to me. There's links in these two articles on my blog to about everything I talked about here today if you want some references.
So you work for Tesla, and just wondering, where does WebAssembly fit within Tesla? or is this a side project?
This is definitely a personal presentation. I'm not representing my work here. I mean, Tesla clearly operates a lot of edge IoT devices. That's what I work on day to day. That's motivating my interest in WebAssembly, not actually using it in any of the systems I build.
Okay, thank you.
So, given the limitations around Tesla, who is going to be the first mover on these IoT Edge use cases, or who is, like, where can we see examples of this being deployed?
I would go look at those runtimes. So, you know, Wasm Time, Wasmer, Wasm Edge. Go look at the companies that are using those. There's Wasm Time's being used in a lot of places. That's what Fastly's using. And also look at that Wasm Cloud project. That's very, very interesting. Yeah, trying to think of some examples that are in Edge IoT. Edge IoT is really, really new. I think one of those runtimes is coming out of IBM, and they're the Edge platform that they developed. I can't say that there's like a canonical example of success there yet. I would say that this is very, very new, very, very promising, but I wouldn't say that, yeah, there's not a canonical, you know, here we did it. Or at least a company being open about that.
I keep wondering if IoT Edge is really, really going to be short-lived as just cloud adoption, you know, takes, you know, the uptick is significant, right? So, I mean, do you think this is something that ultimately WebAssembly would move us, you know, more toward cloud and just like IoT Edge kind of dying off, or any thoughts on the trend around that?
No, I think the trend's actually going the other way, where the IoT Edge is becoming more, IoT, I mean, when I think IoT Edge, I'm really talking critical infrastructure. Electric vehicle chargers, virtual power plants. I mean, these are critical infrastructure now. Those things need to be able to operate autonomously, so you can, you know, charge your car without the cloud. So I think it's going the other way. The other thing driving it, so, you know, rich services at the edge operating autonomously is driving it towards the edge. The other thing is cost. The cloud's expensive. So if you can take advantage of even constrained computing environments to run some of that code, it's essentially free. And you could deliver even more sophisticated services at very low cost.
So looking at EVs, and eventually we're going to have to report a lot of data out of them for the life cycle management of the batteries, right? Do you see this WebAssembly helping with that, with the IoT devices you're talking about in the edge? Because then it can quickly pull that data once you get a charge and tell you what type of charge it was, so you can figure out, you know, how the hard charging and things like that affect.
Without commenting too much about EVs or anything like that, what WebAssembly would allow us to do there is, imagine you could deliver richer services at the edge to, you know, look through data, do anomaly detection, those kind of things, and then only report what's of interest to the cloud, versus reporting all of the data to the cloud, which is quite expensive. The problem there is really the iteration cycle. So you can report all the data to the cloud, people can iterate very, very quickly with low friction. But if you want to do that at the edge, how are you going to do that if you have these kind of long firmware release cycles and with people that are kind of risk adverse? They don't want change because you might have malfunction. So I think that's where WebAssembly might allow this better separation between firmware and software, better interfaces, more security, better testability, those kind of things. So we can be more sophisticated about running those things at the edge. Thank you.